Look at your own hand. Every carbon atom in it should not be here. The physics that assembles carbon leans on numbers finely balanced. Nudge them a few percent and the carbon vanishes, and you vanish with it. This is the fine-tuned universe. A handful of nature's constants sit inside startlingly thin windows, the only windows that permit atoms, stars, and living things. Most of us assume matter is sturdy, that stuff would form under almost any set of rules. It would not. Move the dials a little and the cosmos comes out empty. In 1953, an astronomer worked backward from one fact, that carbon exists at all, and predicted an invisible nuclear resonance no one had ever seen. His name was Fred-Hoyle. Experimentalists at Caltech found that resonance exactly where he said it would sit. Then there is the other number. Empty space should weigh something enormous. It weighs almost nothing, and the gap between the two runs so wide that the textbooks call it, word for word, the worst prediction in the history of physics. The error reaches 120 orders of magnitude, a 1 followed by 120 zeros. So this is where it begins. Start with the carbon, because the carbon is the cleanest case and it is the one you are made of. Where does a carbon atom come from? Not from the early universe. The Big Bang left behind hydrogen, helium, and a trace of lithium, and then it stopped, because it ran out of time and density before it could build anything heavier. Everything past helium was assembled later, inside stars. And here the trouble starts. To make carbon, you have to fuse 3 helium nuclei together. Helium nuclei also go by the name alpha particles, so this route has a name, the triple alpha process. But you cannot fuse 3 things at once. 3-body collisions are absurdly rare. So nature does it in 2 steps. 2 alpha particles fuse into beryllium-8, and then a 3rd alpha strikes the beryllium and completes the carbon. Sounds fine, until you look at beryllium-8. Is beryllium-8 stable? It is not. It falls apart in about 10 to the minus 16 seconds, a tenth of a millionth of a billionth of a second. So picture the scene. 2 alphas briefly stick together into a nucleus that is already flying apart. And a 3rd alpha has to arrive and fuse in that vanishing instant. How does the universe build all its carbon through a doorway that slams shut almost the moment it opens? The answer is a resonance, and it carries the whole story. Think about pushing a child on a swing. Push at random moments and nothing much happens. The energy scatters. But push at exactly the swing's natural rhythm, and the arcs grow with almost no effort. That matching of energies is resonance, and it multiplies the effect enormously. Hoyle's insight was that the fleeting beryllium-8 plus a 3rd alpha would have to hit an excited state of carbon-12 tuned to just the right energy, a rung on the carbon nucleus's internal ladder that sits right where the incoming pieces arrive. Without that rung, the 3rd alpha bounces off and the reaction limps along at a trickle. With it, carbon pours out. Hoyle reasoned that because carbon plainly exists in abundance, that rung must exist too, at a specific energy. And he told the experimentalists where to look. They looked. In 1953, at the Kellogg Radiation Laboratory at Caltech, Dunbar, Pixley, Wenzel, and Whaling found the state. And the following work by Cook, Fowler, Lauritsen, and Lauritsen confirmed its properties. The excited state of carbon-12 sits at an energy of about 379,000 electron volts, 379 kilo-electron volts, above the combined energy of 3 alpha particles. We now call it the Hoyle-state. This is the part that stays with me. A man deduced the internal architecture of a nucleus from the bare fact of his own existence, and the universe agreed. Now, why does this count as fine-tuning rather than clever physics? Because that 379 kilo-electron volts does not rest comfortably in the middle of a broad, safe zone. It perches on a ledge. The rate at which the triple alpha process runs is governed by an equation you can almost read aloud. The resonant rate goes as the radiative width times the alpha particle density cubed times an exponential of minus the resonance energy divided by the temperature. Written compactly, the rate is proportional to gamma gamma times the quantity n alpha over kBt cubed times e to the minus epsilon over kBt. The radiative width, gamma gamma, measures how readily the excited carbon sheds energy and settles into stable carbon. N-alpha is the density of alpha particles, and epsilon, that 379 kilo-electron volts, sits inside an exponential. Why does sitting inside an exponential matter so much? Because an exponential is a brutal amplifier. A small change in epsilon does not nudge the rate, it swings it by factors. Push the Hoyle-state higher, and the exponential collapses the carbon yield toward nothing. The physicist Dean Lee, working on the modern calculation, laid the window out in plain numbers. If the Hoyle-state energy stood at 479 kilo-electron volts or more above the 3 alpha particles, the amount of carbon produced would fall too low for carbon-based life. And in the other direction, if the state sat too low, near or below 279 kilo-electron volts, the reactions would race ahead and burn the carbon on into oxygen, leaving too little carbon behind. A window roughly 100 kilo-electron volts wide, on a nuclear ledge, is the doorway through which every carbon atom in your body walked. What does it mean that the element at the centre of all known chemistry hangs on a resonance perched within a fraction of an emmevolt of the edge that would erase it? Here the story deepens, because that 379 kilo-electron volts is no freestanding dial. The constants underneath it set its value, and that is what a team of nuclear theorists set out to test directly. In 2013, Evgeny Eppelbaum, Hermann Krebs, Timo Lader, Dean Lee, and Ulf G. Meissner published a calculation in Physical Review Letters. They refused to settle for saying the Hoyle-state looks precarious. They wanted to know what would move it. So they built the carbon nucleus from the ground up, from the theory of the strong force, quantum chromodynamics, on a grid. Picture space-time chopped into a cubic lattice, a scaffold of points, spacing just under 2 femtometers, the whole box about 12 femtometers on a side, small enough to hold a nucleus. They ran the simulation on the Jülich supercomputer in Germany, letting the quarks and gluons interact at every node until the carbon nucleus and its Hoyle-state emerged from the equations. Then they did the decisive thing. they turned a dial. They varied the mass of the light quarks, the up and down quarks that make up protons and neutrons, and watched what happened to the carbon and oxygen windows. Their result stands as one of the sharpest statements in this whole field. A change of more than about 2 to 3% in the light quark mass, they found, would lead to problems with the abundance of either carbon or oxygen in the universe. 2 to 3%. Consider a locksmith filing a key. A fraction of a millimetre off on a single tooth, and the key still slides in but will not turn. The quark mass is a tooth on the key that opens carbon chemistry, and the tolerance runs to a few percent. Not comfortable, not robust, a few percent. What would you conclude from a machine whose central gear must be cut to a 2% tolerance, or the whole mechanism jams? I want to pause on how strange the quark mass is, because it sets up something we will return to. The up and down quark masses contribute only about 1% of the mass of a proton. If quarks weigh so little, where does the proton's mass come from? Almost all of it is binding energy, the energy stored in the ferocious gluon field that confines the quarks. Your body's mass, then, is overwhelmingly not the mass of its particles, but the energy of the fields holding them together. The stuff you think of as solid is mostly locked-up energy. Hold that. It matters when we reach empty space. Let me widen the lens from carbon to the ingredients of everything. Before a star can build carbon, it needs protons and neutrons, and their properties form a second knife edge. The neutron weighs slightly more than the proton. By how much? The difference is 1.293 mega-electron volts, about 1 part in 1,000 of either particle's mass. That tiny excess is why a free neutron is unstable and decays, with a mean lifetime of 878.4 seconds, a little under 15 minutes, into a proton, an electron, and a neutrino. Now ask the reversing question. What if the mass difference flipped, so the proton became the heavier one? Then free protons would decay into neutrons. And a hydrogen atom is a single proton with an electron. Lose the stable proton and you lose hydrogen. And losing hydrogen means no water, no organic chemistry, no stellar fuel of the ordinary kind, and no long-lived main sequence stars burning hydrogen for billions of years. The gap that keeps the proton stable amounts to roughly the mass of a couple of electrons. Think of two nearly identical weights on a balance, the difference a grain of sand. Tip it the other way, and the chemistry of the universe empties out. This mass difference is itself downstream of the down quark weighing a touch more than the up quark, and of the electromagnetic energy of the particles. So, once again, we stand on the values of the fundamental constants. A companion danger sits right next to hydrogen fusion, and it has a name worth keeping: the diproton. When two protons meet in the core of a star, they do not normally bind. The strong force nearly holds them, but not quite, and the near miss is what saves us. What if the strong force were slightly stronger, enough to bind two protons into a diproton? Then the very first step of fusion in the early universe would run with no bottleneck, and hydrogen would burn to helium almost explosively, potentially leaving little ordinary hydrogen behind. Estimates of how much stronger the strong force would need to be to bind the diproton vary, and this matters. They genuinely disagree. Some early estimates put it near a couple of percent. John Barrow estimated something closer to 13% to bind the diproton and about 9% to bind the dineutron. Later analyses by MacDonald and Mullen argued you would need a change closer to 50% to burn essentially all the hydrogen away. Keep that spread of numbers in mind. We will return to it, because the disagreement is no footnote. It is a clue about how confident anyone should be. Step back from the nuclei to the star as a whole, because the astronomer Martin-Rees gathered these threads into a single teachable number in his book Just 6 Numbers, published in 1999. Rees calls it epsilon, the efficiency of nuclear fusion, the fraction of mass that hydrogen releases as energy when it fuses into helium. Its value is 0.007, 7/10 of 1%. Why should you care about the third decimal place of a fusion efficiency? Because Rees lays out the consequences on either side. If epsilon read 0.006 instead of 0.007, the binding would be too weak, the deuterium step would fail, and the universe could not assemble the heavier elements. If epsilon read 0.008, binding would be too strong, protons would fuse readily in the Big Bang itself, and the cosmos would burn through its hydrogen at the start, leaving none for stars and water later. A window between 0.006 and 0.008, and we sit in the middle of it. Picture a chemist told that a reaction yield of 0.7% is survivable, 0.6% is sterile, and 0.8% is sterile in a different way. That is the ledge stars stand on. Now the force that arranges atoms rather than nuclei, electromagnetism, whose strength is captured by the fine structure constant alpha, close to 1 part in 137. The fine structure constant can be written as E squared over 4 pi epsilon naught h bar c, the electric charge squared, divided by a bundle of fundamental constants, and it comes out near 1 over 137.036. What does this dimensionless number control? It sets the size of atoms, the energy of chemical bonds, and the height of the electrical barrier two nuclei must climb to fuse. Make alpha much larger, and the electrical repulsion between protons stiffens. Chemistry and fusion both shift character. Make it much smaller, and bonds weaken. Alpha threads between the nuclear forces and the structure of atoms, and the chemistry you depend on lives in the balance. So by now a pattern has formed, and I want to name it fairly, because the fairness is the whole point of this channel. Several independent quantities, the hoyle-state energy, the light-quark mass, the neutron-proton mass difference, the strong coupling, the fusion efficiency epsilon, the fine structure constant, each appears to sit inside a narrow band, outside of which the universe loses carbon, or hydrogen, or long-lived stars, or chemistry. That is the observation at the heart of the fine-tuned universe. Notice what I have not said. I have not said who set the dials, or whether they were set at all, or whether there is only one universe. I have laid out what the measurements show. What the measurements show is that matter is far more sensitive to its constants than a lifetime of solid tables and steady glasses of water would ever suggest. We will return to whether that sensitivity is as tight as it first looks. For now, hold the pattern, because one more number waits, and it is not like the others. It does not govern nuclei or atoms. It governs empty space itself, and it is the largest and strangest tuning of them all. Consider a glass of water sitting on a table. Pour the water out. What is left in the glass? You would say nothing, vacuum, empty space. But quantum field theory says the vacuum is not empty, it seethes. Fields fill all of space, and even in their lowest state, they cannot sit perfectly still, any more than a quantum particle can sit motionless at the bottom of a well. They fluctuate, and those fluctuations carry energy. So, empty space should hold an energy of its own, a vacuum energy. And, by Einstein's relation between energy and mass, that energy should gravitate. How much vacuum energy should there be? When physicists add up the contributions of the quantum fields, using the natural cutoff where the theory is expected to break down, they get an enormous number. Now measure it. The energy of empty space shows up in cosmology as the cosmological-constant, written with the Greek letter lambda, and it acts as a pressure that speeds up the expansion of the universe. In 1998 and 1999, two competing teams measured that expansion using exploding stars. Let me ground this because it actually happened. A particular kind of supernova, type 1a, detonates with almost the same intrinsic brightness every time, which makes it a standard candle. Compare how bright it looks to how bright it truly is, and you know how far away it lies. The High Z supernova search team, led by Brian Schmidt and Adam-Rees, and the Supernova Cosmology Project, led by Saul Perlmutter, hunted these distant explosions, expecting to see the expansion slowing under gravity. Instead, the far supernovae came in dimmer, and therefore farther, than a decelerating universe allowed. The expansion was speeding up. A repulsive energy filled space. The discovery won the Nobel Prize in Physics in 2011, and the culprit was a small, positive cosmological constant. Here is the collision. The measured value of lambda, expressed in natural Planck units, comes to about 10 to the minus 122. The value that quantum field theory naively predicts is of order 1. The gap between prediction and measurement climbs to 120 orders of magnitude, and that gap is what the textbook General Relativity, An Introduction for Physicists by Hobson, Efstathiou and Lazenby calls, verbatim, probably the worst theoretical prediction in the history of physics. Sit with the size of that number. Not a factor of 2. Not a factor of 1,000. A 1 with 120 zeros after it. Picture two surveyors sent to measure the same river, one from the source, one from the mouth. If they came back disagreeing by 9%, you would suspect their instruments. If they came back disagreeing by a factor of 10 to the 120th, you would not question the instruments. You would ask whether they had measured the same river or the same universe. That is the cosmological constant problem, and it is not solved. What does it mean that our best theory of the vacuum overshoots the measured energy of empty space by more zeros than there are atoms in a galaxy? And yet, the universe holds together anyway. Now feel why it matters for you personally, and not just for cosmologists. If the vacuum energy ran as large as the naive calculation says, its repulsion would have been so violent that space would have flown apart before a single galaxy, star, or atom could gather. No structure. If it ran large and negative, the universe would have recollapsed almost immediately. The window in which galaxies have time to form is fantastically narrow compared to the range the number could take. This is the most extreme entry in the whole ledger of the fine-tuned universe, and it is the one that will carry us into the deepest question of all. Keep the 120 in mind. We are going to return to it, and when we do, a physicist named Steven-Weinberg is going to do something almost no one thought possible. He is going to use this very tuning to make a prediction before anyone had measured the answer. I said, matter is more precarious than intuition allows, and I have now laid the ledger open from the Hoyle-state to lambda. The natural next move is to ask how anyone even thinks about numbers like these. What does it mean to say a constant could have been different when we have exactly one universe to look at and cannot rerun it? To go deeper, we need the idea that turned this from a collection of curiosities into a research program. And it starts, oddly, with a question about our own timing. In 1961, the physicist Robert Dicke published a short, sharp argument in the journal Nature. Paul Dirac had puzzled over a coincidence. Certain enormous dimensionless numbers in physics, built from the constants, happened to come out roughly equal. And Dirac suspected the constants must be changing over cosmic time to keep them matched. Dicke offered a quieter explanation. The numbers are what they are, he said, because we could only be here to notice them at a particular epoch, after stars had lived long enough to forge carbon, and before they had all burned out. Our existence selects the moment. It is not that the constants conspire. It is that observers can only find themselves in the conditions that permit observers. That is a selection effect, and it is the seed of everything that follows. In 1973, at a symposium marking the 500th anniversary of Copernicus, the physicist Brandon Carter gave the idea its name. He called it the anthropic-principle, and he chose his words carefully about what it did and did not claim. In its modest form, which physicists call the weak anthropic principle, it says something almost tautological but genuinely useful. Any observations we make are constrained by the requirement that we exist to make them. We should not feel surprised to find ourselves in a corner of space and time compatible with our own existence, because we could not find ourselves anywhere else. Why does something so obvious deserve a name? Because it changes what counts as an explanation. If a constant sits in a narrow, life-permitting window, the anthropic reasoner says, of course it does. No one measures a constant from inside a universe that constant forbids. That is not yet an answer to why the window exists at all, but it reframes the puzzle. In 1986, John Barrow and Frank Tipler expanded the whole subject into a thick, careful book, The Anthropic-Cosmological-Principle, and the term entered the physics vocabulary for good. But an observation selection effect only carries power if there is something to select from. If there is exactly one universe with one set of constants, then saying observers can only exist where observers can exist is true but toothless, because there was never any other option on the table. To give anthropic reasoning teeth, you need a population, an ensemble of regions with different constants, so that selecting the life-permitting ones actually explains something. And that is precisely what a strand of cosmology began to supply, from an entirely independent direction. Not to explain fine-tuning, to explain the shape of the sky. That strand is inflation. In the early 1980s, cosmologists faced puzzles about the very early universe. Why is the cosmos so uniform, the same temperature in opposite directions that could never have exchanged heat? Why is space so flat? The proposed answer was a burst of exponential expansion in the first sliver of a second, driven by a field with a peculiar property, an energy that does not dilute as space stretches. In 1983, andrei-linde proposed a version he called chaotic inflation, and its engine can be written simply. The energy stored in the field, its potential, goes as 1/2 m squared phi squared, 1/2 the field's mass squared times the field's value squared. The field starts high on this potential, and while it sits up there, its energy drives space to double and double and double again, dozens of times over, in an eye blink. How fast does inflation stop? That depends on how gently the field rolls down its hill, captured by what cosmologists call the slow roll parameter, which goes as the Planck mass squared over 2 times the slope of the potential divided by the potential all squared. As long as that parameter stays far below 1, the field creeps and inflation continues. Once the slope steepens, the field tumbles, inflation ends, and its energy converts into the hot particles of the Big Bang. This is standard cosmology, and it has passed real tests. Inflation predicted a specific pattern of tiny temperature ripples in the cosmic microwave background, and those ripples are what the Planck satellite mapped. Then Linde noticed something that changed the scale of the whole picture. In 1986, he showed that inflation, once started, may never fully stop everywhere. Here is the mechanism, and it hinges on a quantum contest. As the field rolls down its hill, two effects compete. Classically, it slides toward the bottom. But quantum mechanically, it also jitters, kicked up and down by fluctuations. In regions where the field sits high enough, the upward quantum jitter per stretch of expansion can exceed the classical roll downward. Written as a condition, when the quantum jump per Hubble time, roughly the expansion rate over 2 pi, grows larger than the classical roll in that same time, the field on average climbs rather than descends. And a region where the field climbs keeps inflating, spawning new inflating volume faster than any patch can settle down. Inflation becomes eternal, self-reproducing, endlessly budding off new regions. Follow what that implies. If inflation is eternal, it does not produce one universe. It produces an unlimited, ever-growing collection of pocket regions, each one a whole observable universe in its own right, budding off from the inflating sea and cooling into a hot Big Bang of its own. Linde described the consequence directly. Instead of a universe with a single set of laws, eternal chaotic inflation predicts a self-reproducing structure in which all possibilities can be realized. This is the multiverse in its cosmological form. And I want to be exact about its status. It is not a separate speculation bolted on to rescue fine-tuning. It falls out of taking a successful theory of the early universe and running its equations forward. Whether it is physically real remains open, and we will weigh that. But it is not idle. It is what the mathematics of inflation does when you do not stop it by hand. Still, eternal inflation by itself only makes many pockets. Do those pockets actually carry different constants? For selection to matter, the pockets cannot all be copies. Something must vary the dials from region to region. And that is where a completely separate field, string theory, entered and supplied a mechanism so vast it strains the language of counting. String theory attempts to describe all particles and forces as vibrations of tiny, one-dimensional strings. And to work mathematically, it requires extra spatial dimensions beyond the three we move through, dimensions curled up too small to see, wound into intricate shapes called Calabi-Yau manifolds. Here is the point that matters for us. How those extra dimensions fold, and how much of various fields, called fluxes, thread through their holes, determines the physics of the large dimensions we live in, including the value of the vacuum energy. Different foldings and different flux threadings yield different effective constants. So the question becomes, how many distinct ways can the extra dimensions be arranged? In 2000, Raphael Bousso and Bousso-Polchinski worked out how the fluxes contribute. The fluxes are quantized. They come in whole number units, like integer numbers of field lines threading each hole. The effective vacuum energy, they showed, is a bare starting value plus 1/2 the sum over all the holes of the flux quanta squared times their charges squared. Written out, lambda effective equals lambda bare plus 1/2 the sum over I of n minus I squared times q minus I squared, where each n is a whole number of flux units and each q a charge. Why does a formula like that produce fine-tuning? Because with 100 or more independent holes, each carrying its own integer, the possible totals form an incredibly dense set of closely spaced values, what they called a discretuum, a near continuum built from discrete pieces. Among that dense forest of possible vacuum energies, some will land, by sheer combinatorics, extraordinarily close to zero. Picture a bank of 100 dials, each clicking to integer settings only. Any single dial is coarse, but combine 100 of them and the number of distinct total readings turns astronomical. And somewhere in that thicket sit combinations that cancel almost perfectly. That is how a theory made of whole numbers can produce a vacuum energy as absurdly small as 10 to the minus 122. How many total arrangements are there? In 2003, work by Cachreau, Kalosh, Linde and Trivedi, known by their initials as KKLT, showed how to stabilize these foldings into long-lived configurations, including ones with a small positive vacuum energy like ours. And the counting of possible stable arrangements, the number of distinct vacua reached staggering figures, commonly quoted as around 10 to the 500, with some estimates in the flux-counting literature running far higher still. Leonard Susskind, in a 2003 paper, gave this vast collection of possible vacua its enduring name, the landscape. He wrote that the number of discrete vacua is astronomical, measured not in the millions or billions, but, in his phrase, in googles or googleplexes. And he drew the consequence plainly and reluctantly. With nothing preferring one vacuum over another, he wrote, the anthropic principle comes to the fore whether or not we like the idea, and string theory provides a framework in which this can be studied rigorously. Now watch the two independent strands click together, because this is the architecture of the leading explanation, and it is worth seeing whole. String theory supplies a landscape of perhaps 10 to the 500 possible sets of constants. Eternal inflation supplies a mechanism to physically realize them, budding off endless pockets, each settling into one arrangement from the landscape. And the anthropic selection effect supplies the reason we find ourselves in a life-permitting one. Observers can only arise in the rare pockets whose constants allow carbon, stars and galaxies. So of course we measure such values, however rare they are, among the whole ensemble. Three fields that grew up separately, particle theory, cosmology, and the old philosophical selection argument, meet in a single explanation for why our constants sit where they do. Before we weigh it, and we will weigh it hard, I want to show you the moment this stopped being philosophy and became physics, because it is the single most important piece of evidence in the whole subject. It is Steven-Weinberg's prediction, and it arrived 11 years before the measurement. In 1987, Weinberg asked a specific question. Suppose the cosmological constant really does vary across a vast ensemble, taking all sorts of values. Among the values compatible with observers, what would a typical one look like? He reasoned physically. Galaxies form when matter clumps under gravity. A large positive lambda pushes space apart and, past some point, prevents matter from clumping at all. No galaxies, no stars, no observers. So there stands an upper bound on lambda, set purely by the requirement that galaxies get to form. He wrote it as a clean inequality. The vacuum density must be less than about pi squared over 3 times the present matter density, times the quantity 1 plus the redshift of galaxy formation, cubed. Plug in a galaxy formation redshift of around 4 or 5, and the bound says the vacuum energy could reach up to a few hundred times the matter density and still permit galaxies. Here is the sharp part. Weinberg reasoned that if lambda varies across the ensemble, it is unlikely to fall much smaller than that bound, because there is no reason for it to. So a typical observer should find a lambda not far below the galaxy formation limit, and crucially, not zero. At the time, most physicists expected the cosmological constant to be exactly zero, cancelled by some undiscovered symmetry. Weinberg predicted a small, non-zero, positive value, of the same order as the matter density. His bound placed it around 550 times the present matter density at most, and his expectation was that we should see something within a couple of orders of magnitude of that. 11 years later, the supernova teams measured it, The observed vacuum energy corresponds to a dark energy about twice the matter density, well inside Weinberg's window and close to the scale his argument favoured. The Planck satellite's 2018 final parameters pin the numbers down. The dark energy fraction of the universe, omega lambda, is 0.6889 plus or minus 0.0056. The matter fraction, 0.315, the expansion rate, 67.4 kilometers per second per megaparsec, the age of the universe, 13.797 billion years. Weinberg himself stayed measured about what it proved. The anthropic bound, he said, is a big improvement over missing by 120 orders of magnitude, but not good enough. Keep both halves of that sentence. It is a real prediction that landed, and it is a man refusing to overclaim it. We will come back to exactly what it is worth. What does it mean that a physicist, by assuming the cosmological constant varies across universes he cannot see, correctly guessed its rough size before anyone measured it, when nearly everyone else expected zero? That is the strongest single card the multiverse plus anthropic explanation holds. Before I let it stand, I owe you the other side, and the other side is substantial. Because a rival camp of physicists has spent years arguing that the whole ledger of tuning is thinner than it looks. Before we get to that argument, absorb the scale of the thing we are proposing, because eternal inflation does not just make different constants elsewhere. Run its logic, and it produces regions so numerous that arrangements of matter repeat. Somewhere, in an unlimited inflating sea, the same configuration of particles that makes up this moment recurs. The same physics that gives us 10 to the 500 vacua also implies copies. I raise this not to dazzle, but to flag a warning we will need. A theory that predicts everything, including endless copies of you, has to answer how it predicts anything specific at all. That difficulty has a name, the measure problem, and it is going to be the hinge on which the whole resolution turns. Keep it in mind. For the past stretch, I've been laying out what the evidence shows, and letting each explanation stand in its strongest form. Now we do the harder thing. We weigh them against each other on the science, and we ask which the evidence actually supports and where each one strains. There are 4 contenders on the table, and they are not equally serious, but each earns a fair hearing. The first is the one we just built, a real multiverse with anthropic selection. Its strengths are genuine. It has a mechanism, eternal inflation, that emerges from a tested theory of the early universe rather than being invented for the purpose. It has a source of varying constants, the string landscape, with its 10 to the 500 vacua. And it holds, in Weinberg's cosmological constant prediction, something almost unique in this field. A case where the framework made a quantitative, falsifiable, forward-looking prediction that later measurement confirmed, against the prevailing expectation of zero. On the evidence, that prediction is the single most impressive result the whole subject has produced. Where does it strain? It strains at testability. We have, in principle, no causal contact with other inflationary pockets. Light from them will never reach us. No experiment can sample their constants. Luke Barnes, who defends the reality of fine-tuning, is explicit that this is the multiverse's central vulnerability, that it may be untestable in principle, and a physical theory whose central entities cannot be observed sits uneasily in physics. And it strains at something deeper, the measure problem I asked you to hold. To say a typical observer sees such and such a value of lambda, you must be able to count observers across the ensemble and compute probabilities. But eternal inflation produces infinitely many pockets, and comparing infinities requires choosing a cutoff, a way of regularizing the count. Different reasonable cutoffs give different, sometimes wildly different, and sometimes paradoxical answers. Alan-Guth, Alexander Vilenkin, Raphael Bousso, and andrei-linde have all worked on this, and there is no agreed solution. Some cutoffs generate the youngness paradox, predicting that we should almost certainly be much younger observers in a much younger pocket, which we are not. Others lead to the Boltzmann-brain problem, predicting that typical observers should be fleeting fluctuations that assemble briefly out of chaos, rather than beings with consistent memories and a lawful past. When your framework can predict such absurdities depending on how you count, you cannot yet claim it robustly predicts our lambda. So Weinberg's success and the measure problem stand in tension inside the same explanation. The prediction worked, but the theory that is supposed to underwrite it cannot yet say cleanly why it worked. That is the honest state of the leading candidate: strong, mechanistic, partially predictive, and unfinished. The second contender takes the opposite tack. There is only one universe, and the constants are not variable at all, but fixed by some deeper theory we have not yet found. On this view, what looks like tuning is really ignorance. When we finally understand the theory underneath the standard model, the values of the quark masses and the couplings, and even lambda, will be derived, not chosen. And the appearance of fine adjustment will dissolve the way many past coincidences dissolved once the underlying law was known. Is there precedent for this? Yes, and it is respectable. The tradition of naturalness in particle physics is exactly the expectation that dimensionless numbers should be derivable and of order 1. And the history of physics is full of quantities that looked arbitrary until a theory explained them. Where does this strain? It strains on delivery. No such theory currently predicts the values in question. Worse, the one place we can test the idea hardest, the cosmological constant, is exactly where the deeper theory program has most spectacularly failed. The natural calculation misses by up to 120 orders of magnitude, the opposite of a derivation that lands on the measured value. And the hierarchy problem and the naturalness puzzle around the Higgs mass, another quantity that looks delicately balanced, remain unsolved despite decades of effort at the Large Hadron Collider and elsewhere. So this contender is aspirational. It could be right, physics has surprised us before. But at present it is a promissory note, not a payment. The third contender is the one I promised we would return to, and it is the one that keeps this from being a tidy story. Perhaps the universe is not as fine-tuned as the strongest claims suggest. This is not fringe. It is a serious, growing body of work, and it attacks the ledger entry by entry. Recall the diproton numbers that disagreed, 2% versus 13 versus 50. That disagreement was the tell. When Barnes and Lewis re-examined the diproton argument in 2015 and 2016, they found that stars keep burning even in a universe where the diproton is bound and deuterium is unbound, contrary to the classic claim that binding the diproton would be catastrophic. Ulf G. Meissner, one of the very authors of the tight hoyle-state result, said it directly about the related deuterium argument. The statement often made that if deuterium is not stable, nuclear synthesis cannot proceed, is obviously not correct. Notice what just happened. The people doing the most careful nuclear calculations are also the ones puncturing the loosest tuning claims. That is science working, not a debunking crusade. Fred Adams pushed further. In 2008, he varied not one constant, but three at once: the gravitational constant, the fine structure constant, and a composite nuclear reaction parameter, and asked what fraction of that parameter space still yields stars that undergo sustained fusion. His verbatim conclusion: a sizable fraction of the parameter space, roughly 1/4, provides the values necessary for stellar objects to operate through sustained nuclear fusion. So, the parameters necessary to support stars are not particularly rare. 1/4 is no knife edge, it is a broad plateau. And the most striking case: in 2006, Ronnie Harnick, Graham Cribbs and Gilad Perez built, on paper, an entire universe with no weak nuclear force at all, the weakless universe. By adjusting other parameters to compensate, they found a cosmos that undergoes Big Bang nucleosynthesis, forms structure and stars, burns those stars for billions of years, cooks elements up to iron, and disperses them in supernova-like explosions. An entire force removed, and a plausibly life-permitting universe still standing. What does it mean that you can delete one of the four fundamental forces and still, apparently, build a home for complex chemistry? It means the window may run wider and shaped differently than the single-parameter horror stories imply. Victor Stenger, in his 2011 book The Fallacy of Fine-Tuning and Its Defenses, pressed the general form of the critique. The standard fine-tuning arguments almost always vary one constant while freezing all the others, which is like measuring the danger of a mountain path by stepping off one edge with your eyes closed, ignoring that you could have shifted your other foot to compensate. Stenger's careful conclusion, and I quote it because its restraint matters: while the precise form of life we find on Earth would not exist with slight changes in these parameters, some form of life could have evolved over a parameter range that is not infinitesimal, as often claimed. Read that twice. He is not saying there is no sensitivity. He is saying the sensitivity has been overstated, and that alternative arrangements might support some complexity we would recognize as life. So where does the third contender strain? Right here. Luke Barnes has answered it in detail, and his answer is not to deny the counterexamples, but to raise the bar. Many of the multi-parameter and alternative universe studies, he argues, check one or two life-permitting criteria, say that stars form, while omitting others that must all hold at once: a stable proton, a long-lived star, a source of carbon, chemical diversity, sufficient time. Loosen one constraint by co-varying constants, he says, and you often tighten another. The weakless universe, for instance, requires its own careful adjustments to reach its life-permitting state. So the real state of the debate is not tuned versus not tuned. It is a genuine, live disagreement about how many independent conditions life requires and how much the constants can co-vary while satisfying all of them at once. That question is not settled, and anyone who tells you it is, in either direction, is ahead of the evidence. The fourth contender is the quietest: brute fact. The constants are what they are. No explanation required, no multiverse, no deeper law, no selection, just the values, full stop. Its virtue is parsimony. It invents nothing. Its vice is that it is explanatorily empty. It declines to engage the question rather than answering it, and it simply absorbs the 120 order of magnitude cosmological constant discrepancy as an unexplained given. Most physicists treat it as a fallback, the position you retreat to only if every other avenue closes. It is not so much a competing explanation as the absence of one. Now let me do what this channel exists to do: state on the evidence what actually holds. The evidence supports a two-part conclusion, and both parts are firmer than the loud versions of this debate on either side. First, some parameters are genuinely, sharply sensitive. This part survives every critique. The hoyle-state energy sits in a window on the order of 100 kilo-electron-volts wide, and the Lattice QCD work of Appelbaum, Krebs, Larder, Lee and Meissner ties that to a 2 to 3% tolerance on the light-quark mass. The neutron-proton mass difference must keep its sign to keep the proton stable. And above all, the cosmological constant sits 10 to the minus 122 in natural units, where naive theory expects order 1. And there is no dispute that a lambda many orders of magnitude larger would have shredded structure before galaxies could form. These are not artifacts of lazy single-parameter reasoning. The critics themselves, Meissner, Barnes-Lewis, do their sharpest work inside exactly these calculations, and the sensitivities remain. Second, and equally supported by the evidence, the degree of tuning has frequently been overstated. The single-parameter method, freeze everything, move one dial, watch disaster, systematically exaggerates the fragility, because it forbids the compensations that covariation allows. Adams's 1/4 of stellar parameter space, the weakless universe, the survival of stars with a bound diproton, these are real results, and they show that some of the tightest-sounding claims do not hold up when you let more than one thing move. Both halves are true at once. Real sensitivity in specific parameters, real exaggeration in the popular accounting. Holding both is not fence-sitting. It is what the papers actually show. And which explanation does the evidence favour for why the sensitive parameters land where they do? Here I will be as precise as the evidence permits. The multiverse plus anthropic framework is the only contender that has produced a confirmed quantitative prediction, Weinberg's cosmological constant, and that is a heavy weight on the scale. The deeper theory program has produced no such prediction, and has failed hardest exactly on lambda. The not-so-tuned camp has genuinely eroded the strongest single-parameter claims, but has not shown that all the sensitive parameters are loose, and it does not by itself explain the cosmological constant. Brute fact explains nothing. On the science, then, anthropic selection within a real ensemble is the leading candidate. But leading is not the same as established. And the reason it is not established is the measure problem. Without a way to compute probabilities over the ensemble, the framework cannot yet be tested cleanly, cannot yet convert Weinberg's one success into a systematic, checkable science, and cannot rule out the paradoxes that different counting schemes produce. Leading but unconfirmed. That is the honest verdict the evidence delivers, and it would be dishonest to sharpen it further than the data allow. Now we reach the edge, and I want to name it carefully, because it is where the science ends and something else begins. Suppose the multiverse is real, the landscape is real, and selection explains why we find life-permitting constants. Step back and ask, why is there an inflating landscape at all, rather than nothing? Why do the equations of string theory, or of inflation, or of quantum fields hold, rather than not hold? The multiverse pushes the question of why there is something structured rather than nothing up one level, from the constants to the framework that generates the constants. But it does not remove the question. And here the equations genuinely stop. There is no measurement that reaches before or beneath the inflating sea. No experiment that can ask why the deepest laws are the laws. This is not a failure of effort. It is where the method itself runs out of grip. So I will do what this channel refuses to fake in either direction. The science can measure the windows, and it has, to many decimal places. The science can, within a selection framework, even predict inside those windows, and Weinberg did. What the science cannot presently do is test the multiverse directly, derive the constants from a deeper theory, or say why there is a lawful, generative cosmos at all, rather than nothing. That last question, why there is something structured rather than nothing, is not answered by this evidence, and I am not going to pretend it is. It is not closed by a maker, and it is not closed by chance. It is open. Naming that openness honestly, rather than papering over it, is the most rigorous thing a scientist can do at this edge. When I first understood this, I had to sit with it for a while, because the temptation to close the gap in one direction or the other runs strong, and the discipline is in leaving it exactly as open as the evidence leaves it. Take a moment with that before I close. Consider what would have to be true for the numbers to come out as they did. Then consider that our best physics can tell you with real precision how narrow the windows are, can even tell you what a typical observer in a varied ensemble should measure, and still cannot tell you why the ensemble exists. That combination, immense knowledge and a clean, well-marked limit, is not a defeat. It is what honest understanding looks like when it reaches its own boundary. Let me bring this exploration to a close. We began with the carbon in your hand and the claim that it should not exist, and we followed the triple alpha process to the Hoyle-state that Fred-Hoyle predicted from his own existence, and Caltech found at 379 kilo-electron-volts. We watched a 2 to 3% tolerance on the light-quark mass drawn from Lattice QCD on the Jülich supercomputer, and the knife edge of the neutron-proton mass difference, and Rees's epsilon at 0.007, and the fine structure constant near 1/137, assemble into the ledger of the fine-tuned universe. We stood before the cosmological constant, 10 to the minus 122, where theory expects order 1, the worst prediction in the history of physics, and watched Steven-Weinberg turn that very tuning into a successful forecast 11 years before the supernova teams and the Planck satellite confirmed a small non-zero lambda. We built the leading explanation from 3 independent strands: Andrei-Linde's eternal inflation, the string theory landscape with its 10 to the 500 vacua, named by Leonard Susskind and mechanized by Bousso-Polchinski and KKLT, and the anthropic selection principle, Brandon Carter named and Robert Dicke foreshadowed. And we tested it honestly against a single universe with a deeper law, against the weakless universe, and Adams and Stenger's case that the tuning is overstated, and against brute fact. Here is what the evidence shows. Some parameters really do sit in narrow, life-permitting windows, and the cosmological constant is the sharpest of them. The degree of tuning has often been exaggerated by moving one dial at a time. And among the explanations, anthropic selection within a real ensemble is the leading candidate, carried above the others by Weinberg's confirmed prediction, yet held short of confirmation by the unsolved measure problem, which blocks a clean test of the multiverse and leaves a residue no current physics can close. The constants hold the values we measure for reasons still undetermined. Whether that something is a multiverse we cannot observe, a deeper theory we have not found, or a fact that needs no cause, the evidence does not yet decide. And the further question, why there is a lawful cosmos at all rather than nothing, lies beyond what any measurement can reach. That is where the evidence leaves us, and it is honest to say so. Return to Martin-Rees for a moment, because epsilon at 0.007 was only one of his 6 numbers, and the other 5 widen the ledger in directions the nuclear physics alone cannot reach. Rees chose 6 because 6 dimensionless quantities, he argued, fix the large-scale character of the cosmos, and each one, moved far from its value, empties the universe in a different way. We have handled epsilon. Consider the number Rees calls n, the ratio of the electrical force to the gravitational force between 2 protons. How large is that ratio? It runs to about 10 to the 36. Gravity, the force that shapes galaxies and holds you to the floor, is weaker than electromagnetism by a factor of a 1 followed by 36 zeros. Why should such an extreme weakness matter? Because gravity's feebleness is exactly what buys the universe its time. Picture a structure held together so gently that it takes billions of years to contract and heat and ignite. If gravity ran even modestly stronger relative to electromagnetism, stars would be smaller, would burn faster and hotter, and would exhaust themselves in millions of years rather than billions. The slow, patient burn of a star like the Sun, 10 billion years of steady output, is a direct consequence of gravity being weak by 36 orders of magnitude. What does it mean that the weakest force we know is the one that grants the cosmos enough time to assemble anything complex at all? Then there is Rees's Q, the amplitude of the ripples in the early universe, the tiny density variations that gravity later grew into galaxies and clusters. Its value is about 1 part in 100,000, written as 10 to the minus 5. This is no abstraction. It is a quantity the Planck satellite, and before it the WMAP satellite, measured directly by mapping the faint temperature differences across the cosmic microwave background, the relic glow of the hot early universe, cooled now to less than 3 degrees above absolute zero and speckled with hot and cold spots at the level of 1 part in 100,000. Those speckles are Q made visible. What happens if Q is different? Make Q 10 times smaller, and the density ripples are too faint. Gravity never gathers them into galaxies, and the universe stays a thin, structureless haze of gas. Make Q 10 times larger, and the ripples turn violent. Matter collapses into enormous black holes, and any gas that survives is bound so tightly that stars, if they form at all, cluster in lethal densities. A universe fit for structure needs Q near 1 part in 100,000, and there it sits. Think of a sculptor working plaster. Too runny, and it will not hold a shape. Too stiff, and it cracks under its own weight. Q is the consistency of the cosmic plaster, and it landed in the workable range. Ries's fourth number is omega, the ratio of the actual density of the universe to the critical density that separates eternal expansion from eventual recollapse. The measured total density sits astonishingly close to critical, which is another way of saying space is very nearly flat, a fact inflation was invented partly to explain. Had omega stood much above 1 in the early universe, gravity would have reversed the expansion and crushed everything back together before stars formed. Had it stood much below 1, the expansion would have run so rapid that matter thinned out before it could clump. The early universe balanced on the flatness line to a precision that, run backward, becomes extraordinary. His fifth number is lambda, the cosmological constant we have already met from the nuclear side, now recognized as the sixth and most dominant component of the cosmic energy budget. And his sixth, d, is simply the number of spatial dimensions, 3. Why 3? In 4 or more large spatial dimensions, the equations governing orbits and atoms change character. Planetary orbits become unstable, spiraling into their star or escaping to infinity. And stable atoms may not form at all. In fewer than 3, complex networks, nerves, circulatory systems cannot cross without intersecting. 3 appears to be the arrangement in which stable orbits and stable atoms and complex structures all coexist. 6 numbers, Ries argued, and each one, moved far, closes a different door on complexity. I want to slow down on the Higgs and the hierarchy problem because it is the entry in this ledger that occupies the front line of experimental physics right now. And it carries the same texture as the cosmological constant, a quantity that looks poised on a razor for reasons no one can derive. The Higgs field fills all of space, and its background value, the Higgs vacuum expectation value, the VEV, is 246 giga-electron volts. Why does that single number matter for you? Because the masses of the fundamental particles scale directly with it. Each fermion, each quark and electron acquires its mass as its coupling to the Higgs field times the VEV over the square root of 2. The mass equals gamma times V over root 2, where gamma is that particle's coupling strength and V is 246 giga-electron volts. The electron's mass, the up and down quark masses that we already saw, must hold to a few percent. All ride on the Higgs vev. Move the vev, and you move every particle mass in the universe at once. How sensitive is the vev? In 1998, the same year the supernovae revealed the accelerating expansion, Vijay Agrawal, Stephen Barr, John Donoghue and David Seckel, known by their initials as ABDS, worked out the window. For the ordinary case, they found that the Higgs vev must stay less than roughly 5 times its observed value, or complex elements cannot form. Push the vev up, and the masses of the light quarks climb. The neutron-proton balance shifts, and the delicate stability of the proton and of the light nuclei fails. Their window, often written as the vev lying between about half and a few times its observed value, is another narrow band. But the hierarchy problem cuts deeper than the anthropic window, and it is worth stating precisely. In quantum field theory, the Higgs mass receives quantum corrections from every particle it interacts with, and those corrections, calculated naively, are enormous, driving the Higgs mass up toward the highest energy scale in the theory, perhaps the scale where gravity becomes strong, some 10 to the 17 times higher than the value we observe. To keep the Higgs mass down at 246 giga-electron-volts, where it sits, the various huge contributions must cancel against one another to something like 1 part in 10 to the 34. Consider an accountant reconciling 2 ledgers, each running to numbers with 34 digits, and finding they must cancel to the last cent, with no rule requiring them to. That is the hierarchy problem. It is the reason physicists built the large-hadron-collider, expecting to find new particles, supersymmetry chief among them, that would naturally protect the Higgs mass. The Large Hadron Collider found the Higgs boson in 2012 at about 125 giga-electron volts, exactly as the theory required, and then, through years of searching, found none of the protective new particles the naturalness expectation predicted. What does it mean that we went looking for the mechanism that would make the Higgs mass natural and found the Higgs exactly where it should be, but no sign of the thing that was supposed to explain it? That empty-handed search matters for our whole story, because it is the naturalness tradition, the second of our contenders, being tested at the highest energies humans can reach, and coming back without the answer it expected. The naturalness principle says dimensionless numbers should be of order 1 and derivable. The Higgs mass and the cosmological constant are the 2 great affronts to that principle, and neither has yielded. Some physicists have taken the Large Hadron Collider's null result as a quiet nudge toward the anthropic and landscape thinking they once resisted, precisely because the deeper theory route has not delivered where it was most confidently expected to. Others hold that naturalness will be vindicated by a theory not yet imagined. The disagreement is real and current, and it sits inside working physics, not on its fringe. Let me take you inside the string landscape one more level, because the phrase 10 to the 500 is easy to say and hard to feel. And the mechanism underneath it is where much of the current controversy lives. When string theory curls its extra dimensions into a Calabi-Yau shape, the shape is not rigid. It has parameters that describe its size and its detailed form, called moduli. And left to themselves, these moduli are free to drift. which would produce forces and effects we do not observe. To make a realistic universe, you must stabilize them, freeze them at fixed values. And that is what the 2003 work of Kacheru, Kalosh, Linde and Trivedi, the KKLT construction, showed how to do. Use the quantized fluxes threading the shape's holes, plus subtle quantum effects to pin the moduli in place, and, crucially, to lift the vacuum energy to a small positive value, like the one we measure. Each distinct way of threading the fluxes and stabilizing the moduli is one vacuum, one possible set of constants, one address in the landscape. Count the ways and, with 100 or more independent holes, each carrying an integer flux, the total runs to the 10 to the 500 figure that has become the landscape's signature. But is the KKLT construction actually valid? Here the field turns on itself, and honesty requires reporting the fight. A vocal group of theorists, pressing what they call the swampland program, argues that stable, long-lived configurations with a small, positive vacuum energy, de sitter vacua like ours, may not truly exist in a consistent theory of quantum gravity at all, that they lie in the swampland of constructions that look fine in approximation but cannot be completed. If they are right, the very foundation of the string landscape as an explanation for our positive cosmological constant falls into doubt. The debate is technical, unresolved, and consequential. The leading mechanism for realizing anthropic selection rests on whether de sitter vacua are real features of the theory or artifacts of an approximation. What does it mean that the mechanism proposed to explain the most fine-tuned number we know is itself the subject of an unsettled argument about whether it exists? Now the measure problem, which I flagged as the hinge and now must open fully, because it is the single deepest obstacle to turning the multiverse from a picture into a testable science, and its pathologies are genuinely strange. The problem is this: eternal inflation, running forever, produces an infinite number of pocket universes, and infinitely many of every kind. To say that a typical observer measures a cosmological constant near the value we see, you must compare the number of observers who see one value to the number who see another. But how do you compare infinities? You have to impose a cutoff, a rule for which pockets to count and in what order, and then take a limit. And here is the trouble. Different, equally reasonable cutoffs yield different answers, and some yield answers that are manifestly wrong. Take the youngness paradox, worked through by alan-guth. Because eternal inflation expands so ferociously, at any given moment there is vastly more volume that has only just stopped inflating than volume that stopped long ago. The youngest pockets outnumber the older ones by staggering factors. If you weight observers by this volume measure, then a typical observer should find themselves in a universe that has only very recently cooled, surrounded by a cosmos far younger than ours, with almost no time for stars and galaxies to have matured. We do not find that. We find ourselves 13.8 billion years into a mature universe. So that measure is wrong, or at least it cannot be the whole story. Consider a census that counts a nation's population by weighting each person by how recently they were born. You would conclude the typical citizen is a newborn, which tells you nothing true about the country and everything wrong about your counting rule. Then the Boltzmann-brain problem, stranger still. In an eternally inflating cosmos, or in any universe that lasts long enough with a small positive vacuum energy, random quantum and thermal fluctuations will, given enough time and volume, occasionally assemble matter into ordered configurations by pure chance, including configurations that momentarily constitute a conscious observer with false memories of a past that never happened. A brain flickering into existence out of the near vacuum and dissolving again. Under certain measures, these fluctuation observers vastly outnumber ordinary observers like us, who arose through the long, orderly cooling of a Big Bang. If the measure says typical observers are such fleeting fluctuations, then it predicts that you, statistically, should be one. Your memories a momentary accident rather than a record of a real past. Since your reasoning about physics would then be untrustworthy, any theory that predicts you are probably a fluctuation undermines itself. Alexander Vilenkin, Raphael Bousso, Andrei-Linde and others have spent years hunting for a measure that suppresses these absurd populations and recovers ordinary observers as typical. And while there are promising candidates, there is no consensus. This is why the measure problem is not a technicality. Until it is solved, the multiverse cannot cleanly tell you what a typical observer should measure, which means it cannot cleanly convert Weinberg's one triumph into a repeatable method, and it cannot rule out predicting nonsense. Take a moment with that. The framework that best explains the cosmological constant is also the framework that, depending on how you count, predicts you are a hallucination. Both of those are consequences of the same equations. Since we cannot observe other universes and cannot rerun our own, how does anyone study these questions at all? The answer is that the alternative universes are simulated, not observed. And it is worth being clear-eyed about what that means and what it can and cannot deliver. Victor Stenger built a toy simulation program that randomly varied constants and checked whether the resulting universe could host long-lived stars, and reported that a substantial fraction of random draws produced viable stars, evidence, he argued, that the tuning runs looser than claimed. Fred Adams, in his 2008 study and in later work on stars in other universes, ran detailed stellar structure calculations across ranges of the gravitational constant, the fine structure constant, and the nuclear reaction rates, mapping out where fusing stars remain possible, and found that roughly 1/4 of his surveyed parameter space still yields functioning stars. And Luke Barnes, in 2018, together with collaborators, took the most ambitious route. They used the Eagle code, a sophisticated cosmological hydrodynamical simulation originally built to model galaxy formation in our own universe, and reran it with the cosmological constant dialed to different values, watching how star formation responded. The Eagle result matters precisely because it complicates the simple fine-tuning story about lambda in a specific quantitative way. What did Barnes and colleagues find? That increasing the cosmological constant by even a full order of magnitude has only a small effect on the efficiency of star formation, and that a significant suppression of the total number of stars appears only when lambda is raised to roughly 30 times its observed value or more. Why does that happen? Because the cosmic star formation rate peaks early, around 3.5 billion years after the Big Bang, before the cosmological constant came to dominate the expansion. Most of the universe's stars had already formed before lambda's repulsion mattered. So, a universe with a considerably larger cosmological constant would still have formed abundant stars. Read carefully. This does not dissolve the cosmological constant problem. The mismatch of 120 orders of magnitude remains untouched, and a lambda 10 to the 120 times larger still forbids all structure. But it does suggest that if you ask specifically how close to our value lambda had to sit for stars to form, the answer is a window perhaps tens of times wide, rather than razor thin, which bears directly on the anthropic prediction. It means a typical observer in the ensemble might expect a lambda somewhat larger than we actually see, a subtlety Weinberg's original estimate anticipated in Spirit and that later authors have sharpened. What does it mean that the number famous as the worst prediction in physics turns out, when you simulate real galaxies, to permit a wider, life-friendly window than the headline suggests, even as its fundamental smallness stays completely unexplained? Return now to the weakless universe, because it deserves its full weight as the boldest counterexample in the whole debate, and because its details show exactly why the tuning question is so hard to close. When Ronnie Harnick, Graham Cribbs and Gilad Perez removed the weak nuclear force entirely in 2006, they did not simply delete it and declare victory. They adjusted the other cosmological parameters, in particular the primordial abundance of matter and the baryon-to-photon ratio, to compensate, and then traced whether such a universe could still assemble the conditions for complexity. Their finding was that it could. Big Bang nucleosynthesis proceeds, producing a mix of hydrogen and helium and, importantly, some deuterium that survives. Structure forms under gravity. Stars ignite and burn, not through the weak force-mediated proton-proton chain that powers our Sun, but through other channels, and they burn for billions of years. Heavier elements are cooked up through the periodic table toward iron, and stellar deaths disperse those elements into space, where they might, in principle, assemble into complex chemistry. An entire fundamental force, one of the four absent, and a plausibly habitable cosmos still standing. Think of a bridge engineered with 4 cables that you assume are all load-bearing, and then discover that by retensioning the remaining 3, you can remove one cable entirely and the span still holds. That is what the weakless universe demonstrates about the weak force, and it lands a serious blow to any claim that our specific set of 4 forces is uniquely necessary for complexity. But Barnes's rejoinder applies here with full force, and fairness demands it. The weakless universe is no free lunch. It required its architects to tune other parameters to keep it viable, trading a constraint on the weak force for constraints elsewhere. It demonstrates that the weak force specifically is not indispensable, which is genuinely surprising and genuinely important. But it does not demonstrate that no tuning is needed. it relocates the tuning rather than abolishing it. And this is the pattern that runs through the entire not-so-fine-tuned literature. Loosen one dial by allowing others to move, and the burden often shifts to those others. Whether across the full space of all constants moving together there is a broad and easily reached region of viable universes, or only scattered, narrow islands connected by careful compensations, is the unsettled heart of the matter. Stenger reads the evidence as broad regions. Barnes reads it as scattered islands. And the honest report is that the full, multi-dimensional survey that would settle it has not been done, because the space is too large, and the criteria for what counts as life-permitting are themselves contested. What does it mean that after decades of argument, the most basic version of the question, how much of the space of possible physics permits complexity, remains genuinely open because the calculation is too big to finish? There is a subtlety in Adams's 1/4 figure worth drawing out, because a number like that can mislead if taken alone. When Adams says roughly a quarter of his parameter space yields functioning stars, that quarter is measured over the specific ranges he chose to scan, and over the 3 parameters he varied together. Change the ranges, or vary a different combination of constants, and the fraction changes. This is not a criticism of Adams, who was careful about exactly this. It is a caution about what any such fraction can mean. There is no natural, agreed-upon probability distribution over the possible values of the constants. No rule that says the fine structure constant is equally likely to take any value between here and there. Without such a distribution, saying a quarter of the space is habitable is a statement about a chosen slice, not about how probable a life-permitting universe is in any absolute sense. And this connects straight back to the measure problem. The reason we cannot say how surprising our universe is the same reason we cannot say what a typical observer should measure, because in both cases we lack an agreed way to assign probabilities across the possibilities. The fine-tuning debate and the measure problem are, at bottom, the same unsolved problem wearing 2 faces, one turned toward particle physics and one toward cosmology. Let me put the Friedmann-equation on the table now, because it is the machinery that turns the value of the cosmological constant into the fate of cosmic structure, and it makes the stakes concrete. The expansion of the universe obeys, in its standard form, the relation that the square of the expansion rate, the Hubble parameter, h, equals 8 pi g/3 times the density of matter and radiation minus a curvature term plus the cosmological constant term, lambda c squared over 3. In words, the rate at which space expands is set by a tug-of-war, matter and energy pulling the expansion down through gravity, curvature adjusting it, and the cosmological constant, if positive, pushing it up and, uniquely, refusing to dilute as space grows. That last property is the crux. As the universe expands, matter thins out, its density falling as volume grows. So the matter term in the Friedmann equation weakens over time. But the cosmological constant term stays constant, because it is the energy of space itself, and space is exactly what there is more of. So there comes a moment, and for our universe it arrived a few billion years ago, when the constant term overtakes the matter term, and the expansion, which had been slowing, begins to accelerate. This is what the supernova teams caught in 1998. The Friedmann-equation tells you why a small lambda is compatible with a long era of structure formation. Matter dominates early, when galaxies form, and lambda takes over only late. And it tells you why a large lambda would be catastrophic. Its term would have dominated from the start, tearing space apart before matter could gather. One equation, and it holds the whole drama of why the cosmological constant smallness buys the universe its structured middle age. I return often to a single juxtaposition, because it captures the strangeness of this entire subject better than any argument. The cosmological constant is at once the worst prediction in the history of physics, our theory of the vacuum overshooting the measured value by up to 120 orders of magnitude, and the reason galaxies had the billions of years they needed to form before the expansion ran away. The same number carries our deepest failure of understanding and our existence in one breath. This is the part that stays with me. Not the size of the error, which is merely enormous, but that the number we understand least well is the number our presence depends on most delicately. What would you conclude from evidence like that? Hold the question. Do not rush to answer it, because the discipline of this subject is precisely the refusal to convert wonder into a verdict. Consider, too, how much the fact of our own existence has been made to do in this field, methodologically, because it is genuinely unusual in physics. Fred-Hoyle inferred a nuclear resonance from the bare fact that carbon exists. Robert Dicke inferred the epoch of the universe from the fact that observers require carbon and time. Steven-Weinberg inferred the rough size of the cosmological constant from the requirement that galaxies form. In each case, a scientist reasoned from "we are here" to "the physics must allow it," and extracted a real, checkable consequence. That style of reasoning, from existence to constraint, is what the weak anthropic-principle formalizes. And it is not mysticism. It is a selection effect. The same logic a biologist uses when noting that any planet with observers must have had a stable climate long enough to produce them. What does it mean that the simple fact of our own presence, used as a premise, has repeatedly yielded correct physics? It means, at minimum, that existence is genuinely informative about the constants, that we are a data point, and a stringent one. It does not tell us why the constants permit that data point. That further step, from existence is informative to here is why the universe permits existence, is exactly the step the evidence does not license. And watching careful physicists refuse to take it, Weinberg calling his own success not good enough, is watching scientific discipline at its most demanding. There is one more strand to weave before the threads come together, and it concerns what the confirmed parts of this picture rest on observationally. Because it would be easy, amid landscapes and multiverses, to forget how much of this is anchored in hard measurement. The cosmic microwave background, mapped by the WMAP satellite in the 2000s, and then to exquisite precision by the Planck satellite, whose final parameters were released in 2018, is a photograph of the universe when it was 380,000 years old, and its pattern of hot and cold spots encodes the geometry, composition, and age of the cosmos. From it, we know the universe is 13.797 billion years old, that it is spatially flat to high precision, that ordinary matter is about 5% of the total, dark matter about 26%, and dark energy, the cosmological constant made manifest, about 69%. Omega lambda of 0.6889. Inflation predicted specific statistical features of those spots, that they should be nearly but not exactly the same size across all scales, tilted by a small calculable amount, and the Planck data match that prediction well. So the base of this whole edifice, the accelerating expansion, the flat geometry, the inflationary origin of structure, is not speculation. It is among the best measured knowledge in all of science. The speculation begins only where the measurements stop, at the question of whether the inflation we have strong evidence for continues eternally elsewhere, and whether the vacuum we inhabit is one draw from a landscape of many. That boundary between the firmly measured and the currently untestable is the boundary this whole subject lives on, and keeping it sharp is the difference between science and story, which brings the competing explanations into their final relation, seen now with all the machinery on the table. The multiverse with anthropic selection is mechanistically the richest. Eternal inflation from tested cosmology, a landscape from string theory, selection from an uncontroversial logical principle, and one confirmed prediction in Weinberg's lambda. But three unfinished problems shadow it, each of which we have now examined. The measure problem that blocks clean probabilities, the swampland doubt about whether its landscape of de sitter vacua even exists, and the in-principle difficulty of ever observing another pocket. The single universe deeper theory hope has precedent and elegance on its side, but no delivered prediction, and a spectacular failure exactly at the cosmological constant, compounded now by the Large Hadron Collider finding the Higgs without the naturalness-restoring particles that were supposed to accompany it. The not-as-fine-tuned position has landed real, damaging hits on the loosest tuning claims: the weakless universe, Adams's stellar quarter, the Eagle lambda window, Barnes and Lewis on the diproton, Meissner on deuterium, and has correctly exposed the single-parameter method as systematically misleading. Yet it has not shown that all the sensitive parameters are loose, and it cannot by itself explain the smallness of lambda. And brute fact remains what it always was, the refusal of the question dressed as an answer to it. So the evidence, weighed honestly, supports a layered conclusion rather than a slogan. It is settled that specific parameters, the hoyle-state energy, the light-quark mass, the proton-neutron mass difference, the Higgs vev, and above all the cosmological constant, are genuinely sensitive, that real physics breaks in real ways when they move far. It is equally settled that the popular accounting has overstated the tuning by moving one dial at a time, and that letting constants co-vary widens some windows substantially. It is best supported, though not confirmed, that if the sensitive constants land where they do because of anything at all rather than for no reason, anthropic selection within a real ensemble is the leading candidate, carried above its rivals by the one prediction any of them managed to make and get right. And it is beyond present reach, not merely unknown, but currently untestable, whether that ensemble is physically real, whether a deeper theory will one day derive the constants instead, and, at the deepest level, why there is a lawful, structure-generating cosmos at all, rather than nothing. That final question is not answered by this evidence in either direction, and the integrity of the whole enterprise depends on saying so plainly. Let me bring this exploration to a close. We began with the carbon in your hand and the claim that it should not exist, and we followed the triple alpha process to the Hoyle-state that Fred-Hoyle predicted from the bare fact of his own existence, and that Caltech confirmed in 1953, sitting at 379 kilo-electron-volts within a window barely 100 kilo-electron-volts wide. We traced the light-quark mass to its 2 to 3% tolerance in the Lattice QCD work of Eppelbaum, Krebs, Larder, Lee and Meissner on the Jülich supercomputer. And we walked the rest of the ledger, the neutron-proton mass difference of 1.293 mega-electron-volts, Rees's epsilon at 0.007, and his n at 10 to the 36, and his q at 1 part in 100,000, the fine structure constant near 1/137, the Higgs VeV at 246 giga-electron-volts with its hierarchy problem, and the cosmological-constant 10 to the minus 122, where theory expects order 1, the worst prediction in the history of physics. We watched Steven-Weinberg turn that very number into a successful forecast 11 years before the supernova teams and the Planck satellite confirmed a small, non-zero dark energy at 69% of the cosmos. We assembled the leading explanation from andrei-linde's eternal inflation, the string landscape stabilized by KKLT and named by Leonard Susskind, the flux discretuum of Bousso and Polchinski, and the anthropic selection principle that Robert Dicke foreshadowed and Brandon Carter named. And we tested it, without mercy and without prosecution, against the deeper theory hope, against the weakless universe, and Adams and Stenger and the Eagle simulations, against the measure problem with its youngness paradox and its Boltzmann-brains, against the swampland doubt, and against brute fact. Here is what the evidence shows, stated as plainly as the data permit. Some of nature's constants sit in narrow, life-permitting windows, and the cosmological constant is the sharpest of them, unexplained by any theory to a degree of 120 orders of magnitude. The degree of tuning has often been exaggerated by the habit of moving a single constant while freezing the rest, and letting them vary together widens several of the windows. Among the explanations for why the genuinely sensitive constants land where they do, anthropic selection within a real ensemble is the leading candidate, lifted above its rivals by Weinberg's one confirmed prediction, yet held short of confirmation by the unsolved measure problem, the unresolved question of whether the landscape's vacua truly exist, and the impossibility so far of observing another pocket of the cosmos. The constants hold the values we measure, and those values are what allow the carbon, the stars, the galaxies, and the observer now considering them. Whether that something is a multiverse, forever beyond our instruments, a deeper law we have not yet found, or a fact that requires no cause, the evidence does not decide. And the furthest question of all, why there is a lawful universe at all, rather than nothing, lies past the edge where every measurement runs out. That is where the science ends, and it is honest to let it end there, neither closed nor pretended away. If you have found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds who are willing to follow the evidence all the way to its honest edge and sit with what remains open. The constants sit where they sit, measured now to many decimal places, understood in their consequences down to the resonance that forged the carbon speaking these words, and silent still on the one question that lies beneath them all, waiting in the narrow window that lets everything you have ever known exist at all.